So now we've evaluated what causes magnetic fields, and we start to take a look at the way those magnetic fields interact with different types of matter. But what we really need to know is what it is that those magnetic fields cause. And what they cause is a magnetic force on moving charges. We can quantify this for any individual charge through this equation, where the force caused by that magnetic field is equal to the magnitude of the charge times the speed of that moving charge, because it must be moving, times the magnitude of the magnetic field, and then times the sine of theta, because the magnetic field must have a component perpendicular to the motion of the charge. And just like any other force, this force is measured in newtons. So let's consider this then and evaluate whether this particle that we'll be following will experience a magnetic force. So first, in order to experience a magnetic force, there must be a magnetic field. So if the magnetic field equals 0, then the magnetic force will also equal 0. So in this case, let's set that magnetic field as being to the right in the screen. Next, this particle that we're looking at must also have some charge. So Q is not able to equal 0. So far, we have that we must have a magnetic field, so B may not equal 0, and we must also have a charge. That magnetic field must be interacting with a charge, so Q is not able to equal 0. Next, that charge must be moving. V cannot be 0, or FB will equal 0. So we have to set this positive charge moving through the magnetic field. We only get a force when that magnetic field is interacting with a moving charge. But there are all these different potential ways that this positive charge could be moving through this magnetic field. We want to know which ones will create a force, and that's when we use the sine theta. We do not want that sine theta to equal 0, and sine theta equals 0 at 0 and at 180 degrees. So we want that moving charge to be moving through the magnetic field, not with an angle of 0 degrees or 180 degrees to the magnetic field. So that would be either along in the same direction as the magnetic field or completely against it. A good way to evaluate this visually is to look at whether the vectors cross magnetic field lines. As we look at V 0 degrees and V 180 degrees, we see that they cross no field lines, so there is no force. The vector at 30 degrees does cross a few lines, so it will have a weak magnetic force on it. Whereas the vector at 60 degrees does cross 5 lines, so it has a stronger magnetic force on it than the vector at 30 degrees. And the vector at 90 degrees crosses 6 field lines, so it has the maximum magnetic force on it. So when we're looking for motion of charge, we're going to be looking for that motion of charge to be ideally 90 degrees to the magnetic field, in which case the sine of theta becomes 1, and the force from the magnetic field equals Q times V times B. But then that brings up the question, in what direction does that magnetic force point? And to determine that, we can use the right-hand rule again. In this case, we are maintaining that the movement of charge is still our thumb. But we must remember that this is the movement of positive charge for conventional current. So the movement of positive charge goes with our thumb, and our fingers are once again, just as we used the right-hand rule previously, going along with the magnetic field. As you do this, with positive charge along your thumb, fingers along the magnetic field, your palm from your right hand will point in the direction that the force pushes. When you push something, you push with the palm of your hand. So in this case, as we put our thumb up and our fingers to the right, our palms are facing in towards the screen. So the force from this magnetic field on this positive charge moving upward is into the page or into the screen. That magnetic force, QVB sine theta, is also a centripetal force, so we can set it equal to the centripetal motion equation, force equals mv squared over r. Let's observe the circular motion of a charge moving in various magnetic fields. When charge is moving upward with a magnetic field into the page, that will cause a force to the left on that positive charge. This means as it moves upward, it will be forced to the left until all of its upward motion has been cancelled by a force towards the center of the circle. Now it only has a left component of motion. So as it is moving left in a magnetic field pointing into the page, it is experiencing a force downward. And the same thing continues as it circles around to the left side, whereas it's moving down, it feels a force to the right. And at the bottom, whereas it's moving to the right, it feels a force upward. This will bring it back to its original position, completing the circle. The radius, r, of that circle is the r from the centripetal force equation. So when we have a magnetic field into the page and a charge moving within the plane of the page, it's going to create circular motion in the plane of the page. However, if the magnetic field and the motion are both in the plane of the page, that's going to create circular motion that is perpendicular to the plane of the page. We can see here, as we have a positive charge moving upward and a magnetic field to the right, that'll create a force into the screen or into the page. This will create circular motion that wraps around behind the magnetic field into the screen, then comes back out towards us, and then back to its original position. The loop here would go away from us, with the positive charge being at its closest point where it started. Another example would be to have the magnetic field going downward and the charge to the right. In this case, the charge moving rightward in the downward magnetic field experiences a force into the page, and once again undergoes circular motion until it returns to that original position. We do want to keep in mind that the direction of motion here for a positive charge is opposite of what it would be for a negative charge. Negative charges would circle in the opposite direction. So if we return to that first example with the magnetic field into the page, we would have a negative charge moving to the left instead of the positive charge moving to the right. This would cause a force upward in the page and would cause a clockwise circle for that negative charge, as opposed to the counterclockwise motion experienced by that positive charge. Just like individual charges, wires carrying current through a magnetic field will also experience a force along the entire wire. The equation for this is current times the length of the wire times the magnetic field times, once again, the sine of theta. This is actually identical to the QVB sine theta equation in terms of units. The rest of the same concepts do apply to the magnetic force on a wire. However, this is often easier to confuse what type of force will be felt by the wire from that magnetic field. So let's evaluate which points will feel a translational magnetic force from wire W. First, we have point X along wire X. We have point Y along wire Y, which is at an angle 30 degrees from being parallel with wire W. And point Z in wire Z, which is aligned perpendicular to wire W. So let's first describe that magnetic field from wire W. As we use our right hand, thumb pointing upward with the current through wire W, and grab that wire, our fingers would go into the screen on the right hand side of the wire and come out of the screen on the left side. That describes a magnetic field like this, that as we look at from above is going counterclockwise. Then we look at the charges in wire X, Y, and Z and how they are affected by magnetic field W. So let's look at the direction of the magnetic field at each point. At point X, it is coming out of the screen. Point W, it's going into the screen. And at point Z, it is moving to the left in the screen. So at point X, along wire X, we have the current moving upward and the magnetic field out of the page. Since these are perpendicular to each other, there will be a force. And as we use the right hand rule, we can find that that force will be to the right. Next, at point Y, we see the magnetic field going into the screen and the current moving up and to the left at a 30-degree angle from being vertical. This, however, does not mean it is not 90 degrees from the magnetic field. It might be only 60 degrees from the x-axis as we look at the screen. But the z-axis, which goes into the page along the magnetic field from W, is at 90 degrees to the current through point Y. This means we will have a force, and that force will be to the left and down 30 degrees below being horizontal. Point Z, on the other hand, has a magnetic field to the left and current to the right. Those are 180 degrees away from one another. When we take the sine of 180, we get 0, so there will be no force on wire Z. Now let's practice the information we've reviewed about magnetic fields. Take a look at question 1 and choose an answer. The correct answer is C, into the page. The apparatus as drawn would create an electric field that would point towards the bottom of the screen, because that's the direction of force on a positive charge, moving away from the positives at the top and towards the negatives at the bottom. So we have a force downward on the charge as it moves through the apparatus. To not be deflected, we need a net force of 0 on this charge, so we need another force upward. To determine which way we need the magnetic field then, we would use the right-hand rule, going backwards from knowing the force and the motion of charge to determine that magnetic field. With the positive charge moving to the right as our thumb, and our palm facing upward to represent that force, our fingers point into the screen representing the magnetic field. So we would need an into the page magnetic field for this charge to go through undeflected. Now take a look at question 2 and choose your answer. The correct answer to question number 2 is B. We have a 2 millicoulomb charge traveling 10 meters per second near a wire carrying a 5 amp current. If the charge's velocity and the wire's current are perpendicular when they are 1 centimeter apart, what is the magnetic force on the wire at that moment? To determine this force, we must first determine the magnetic field at this point 1 centimeter away from the wire. Then we must determine the force on that 2 millicoulomb charge as it travels through that magnetic field. This will tell us the force on that charge as it travels near that magnetic field. However, the question asks us about the magnetic force on the wire at that moment. And here's where it's important to remember Newton's third law. For every action there is an equal and opposite reaction. If the source of magnetic field is exerting a magnetic force on a moving charge, then that same force is being felt by the source of the magnetic field in the opposite direction. So by calculating the force on the charge, we also calculate the force on the wire. Since this is a straight wire, and we do not have our donut-shaped circular loop of wire, we do have pi in our magnetic field equation. For the magnetic force, we will be using the QVB sine theta version of the equation, as we're calculating the force on that charge. Rearranging gives us an equation that looks like this, though you could also calculate the first part for the magnetic field and then calculate the second for the magnetic force. Which brings you to this point. Here, it would be very helpful to cancel out any numbers that you can, for instance the 4 pi and the 2 pi to give you 2. And various other simplifications that can get you to 25 times 2 times 10 to the negative 7 times 5 over 10 to the negative 2. And the sine of 90 has become 1. And once you simplify that, you get answer choice B. Now we've gone over quite a bit of information about the magnetic field's forces caused by them. So we should review them and make sure we have the key concepts down. Because magnetic fields, as complicated as they can be, have very few rules that guide them both in their creation and their application. The recognizable conditions for magnetic fields mainly fall into moving charges. Moving charges are necessary both to create a magnetic field and to feel a force from that magnetic field. Let's begin reviewing by looking at magnetic field lines. In permanent magnets, the magnetic field lines exit the North Pole and re-enter the South Pole. Those lines will specifically connect points of equal magnetic field strength. And the strength of the magnetic field is represented in those lines by the density of the field lines. The closer the lines are together, the stronger the field. And that magnetic field strength can vary in two ways. First, as you get farther from the source of the magnetic field strength goes down. This works both for a permanent magnet and for a magnetic field caused by a wire. And also for the magnetic fields caused by current-carrying wires, the magnetic field increases along with the current. And finally, the last thing we really want to keep straight are the right-hand rules. First, we want to be familiar with the right-hand rule for creating a magnetic field around a wire. In these cases, thumb will, as always, indicate the direction of positive charge movement, and our fingers will wrap around the wire in the same direction as the magnetic field. This works for both straight wires and circular loops of wire. Next, we want to be familiar with the right-hand rule in terms of its effect on a moving charge. This is represented mathematically with F equals QVB sine theta, where that sine theta indicates that we need to have a perpendicular component between the motion and the magnetic field in order to get a force. To apply the right-hand rule here, we once again use our thumb for the direction of positive charge movement. We use our fingers to represent the magnetic field again, and now the push is with our palm, because that's the side of your hand you push with. We do want to remember that the opposite happens when there is a negative particle instead of a positive particle. Here we see a positive particle experiencing a force from a magnetic field that is to the right. However, if that were a negative particle, the force would not be to the right, but given the same motion, it would be to the left. Congratulations! Now with the completion of the magnetism review video, you've tackled one of those intimidating physical science topics, and you're that much closer to getting into medical school. Best of luck to you.